So let's see how the dimensions of valves can be worked out. That is called valve sizing. And also when it comes to valve open area, not only the dimensions of the valve, but also the lift also matters. Accordingly, we need to work out what should be the maximum lift also. So to understand the amount of mass induced per cycle in the induction process, we could mathematically represent the amount of mass induced per cycle like this: m dot, that is in mass flow rate, into d theta, integration over the intake valve opening angle and intake valve closing angle, divided by 1 upon omega. So this, of course, you can find from the basics. We know that dm equals m dot dt, and omega equals d theta over dt. So if you combine these two equations and get rid of dt term, because the time is a parameter that we do not know. Other parameters we know, the thetas, because it depends on the valve timing. And an expression for m dot we found earlier, the orifice for equation. Accordingly, if you can work out average effective intake flow area, A dash F, we can again mathematically find it and represent this equation. This is instantaneous area, and this is the average area. And then we can represent the volumetric efficiency, which we know that it is mi over rho I d Vd, that is displaced volume. Mi we could replace from this, and AF you could replace from this. So then we can get this relationship like this. And the integration of this equation over across the inlet valve opening and inlet valve closing would give us then the volumetric efficiency. And if there is no black flow, so we could assume that all gases are air. Then we could say rho over rho I, or C over Ci, the same one. And then if you go into the critical conditions, limiting case, where the flow becomes choke, we know that the flow does not depend on the pressure ratio. Accordingly, we can simplify the integration like this. The pressure ratio does not depend on the crank angle. Therefore, the integration becomes very simple, and the neta V will become this. And to further look into this, if we define Mach index, that is cycle averaged Mach number. So if cycle average Mach number, that indicates or characterizes the average speed of intake gas required in order to fill up the entire cylinder under a particular mean piston speed. So we could represent Z like this. Again, we can find this is a Mach number on average quantities. So the speeds that we use are average speeds. The average speed, the mass flow rate, whatever comes in through the valves, should occupy the displaced volume of the cylinder. Accordingly, this is the amount of mass flow rate comes in the system, and this is the mass flow rate into the cylinder. And if rho is constant, then you can equate this to this. And accordingly, if you substitute these values into the definition of Mach number, then you will get this. That is U over C is Mach number. So accordingly, in terms of Z, we can represent the volumetric efficiency. And for example, for gamma equals 1.4, this equation becomes this one. Neta V equals 0.58 into theta inlet valve closing timing minus inlet valve open timing divided by 5, 1 upon Z. So that is the volumetric efficiency. when the flow becomes choke. Z is the Mach index. This chart shows us the volumetric efficiency, variation of volumetric efficiency against Z, the Mach index. So these are experimental values. And this is the plot of the equation that we considered, eta V, for a situation where the inlet valve duration, open duration divided by pi equals 1.3. Accordingly, volumetric efficiency becomes 0.75 divided by Z. So if you substitute these values, eta V becomes 0.75 divided by Z. So that is this variation. So it is not exactly the real situation because this is one-dimensional simplified model using ideal gases, but it is somewhat close to understand the real situation. And if you look at the real values, experimental values rather, then it is always good to have high volumetric efficiency. So volumetric efficiency around 80% could be achieved if the value of Z is, let's say, around 0.6. So in this region, so 0.5 to 0.6. So you get the maximum volumetric efficiency. So it is good to have this Mach index around 0.6. And again, we consider this is a limiting condition where the flow is choked. But if it is not choked, of course, volumetric efficiency is always better. Usually, the inlet valves can be sized based on the maximum piston speed for which the engine is designed. So based on these observations, if you can assume that for design purposes, Z has to be less than 0.6. So Z less than 0.6 gives you the maximum volumetric efficiency under choked condition. That means it is, if it is not choked condition, it will always be better. So the average effective area we could write down based on this relationship, the definition of Mach index. So if this Z it should be less than or equal to 0.6, then this equation, this is the normal area becomes the intake area for intake stroke. We obtain this relationship. And for exhaust also, we can do the same thing. Only thing is the area will become exhaust area, average exhaust area, exhaust valve open area rather. And this is the speed of sound under exhaust air condition. And if you divide these two, average area in intake and average area exhaust, then this will be approximately equal to the ratio of CI over CE. And we know that C equals square root of gamma RT for ideal gases. Accordingly, the C's can be represented in terms of T, square root of T. So the temperature ratio would govern the required area ratio, exhaust to intake. And if you further look at this little in detail, we know that the temperature of exhaust gases are always higher than the temperature of intake gases. Accordingly, the ratio between Ti over Te, or the ratio of Ti over Te, is always less than 1. Accordingly, we can say the area of exhaust valve open area on average basis should be smaller than the intake valve open area. So that is the observation that we can make based on this analysis. And accordingly, when it comes to design of engines, we'll have to make it a point that always we have to have a larger diameter for intake valve compared to the diameter of the exhaust valve. Typically in practical engines, the ratio is in between 0.7 to 0.8, 0.7 to 0.8. And so when it comes to implementation of this concept in real engines, there are several limitations. That is mostly the cross-section area of the cylinder would limit the size of the valves, so you can't go beyond that. in general situations. Accordingly, it is quite customary to represent these sizes as a function of the diameter of the cylinder or the bore of the engine. And also, it should be always important to make sure that the size that we could use would discourage the system to achieve sonic conditions. As I just said, if it is an open combustion chamber like this, then the size of the valves are limited by the diameter of the bore, and the valves can be placed like this. This is the intake valve, 0.44B, and this is the exhaust valve, 0.38B. And sometimes you can have one large intake valve and two exhaust valves like this to utilize the available area to the maximum, or sometimes you can use two inlet valves and two exhaust valves. So if you use two valves, one valve for inlet and one valve for exhaust, there's a lot of unused area as far as the placement of valves are concerned, but this is quite filled, and this is also the area is filled by the valves. So the larger the valves, better the volumetric efficiency would be. And also people use various different other approaches to increase the cross-section area. For example, rather than having open flat combustion chambers like this, or the heads like this, you could use plane-proof type or hemispherical type combustion chambers like this, where you can increase this valve area available to place the valves. So that can also enable us to have larger diameter valves. These are some of the typical values of the inlet and exhaust valve at different mean piston speeds for different combustion chamber shapes. So these are the shapes. We'll discuss details about these different shapes when we talk about combustion. And the inlet and exhaust valves are defined in terms of the bore, the size, the diameter of the cylinder. The design objective is to induce maximum amount of air into the cylinder during the intake stroke under wide open throttle conditions. That indicates that we're looking for maximum possible volumetric efficiency, because the indicated power is directly proportional to the mass flow into the system. And also in the intake system, we need to make sure that the air and fuel mixes well during the induction process, particularly in spark ignition engines. And also we'll need to create certain turbulence flow patterns in order to enable proper mixing of air and fuel during the intake process as well as compression process. So if you can recall, we generate swirl and tumble flow in the intake system just to enable that. So those are the important things that we need to consider when it comes to design of intake system. And as we just saw, common approach is to have multiple valves in the cylinder. And but when you have multiple valves and large valves, the weight of the engine increases, and there are positives and negatives of increasing the size of the valves. Accordingly, there's another approach of strategically controlling valves instead of having static valve open close timing, which we call variable valve timing, which enables us to ensure the highest possible volumetric efficiency under different engine operating conditions, speeds as well as loads. Just to understand the importance of variable valve timing, first let's look at this chart. That is volumetric efficiency against the engine speed. So these are some experimental results under different valve timing conditions. The valve lift is kept at 8.5 in this particular experiment, millimeters. And the timing is given in terms of inlet valve open timing, inlet valve closing timing, exhaust valve open timing, and exhaust valve closing timing. So that is what is given here. Inlet valve open before top dead center. Inlet valve open angle is given as before top dead center. inlet valve close timing is given by after bottom dead center. So that is the bottom dead center, this value after bottom dead center. And exhaust valve open timing is again before bottom dead center. So this angle, and exhaust valve closing timing is after the top dead center. That is this value after the top dead center. So those are the values given here, over here. So this one, you can, if you concentrate on inlet valve open and inlet valve close timing for the moment, you can see over here, the inlet valve is closed at the bottom dead center. This angle is 0, means there's no duration after the bottom dead center. Therefore, the valve is closed at the bottom dead center. And if the valve is closed at the bottom dead center, so these are the experimental values, these triangles. So this is the triangle. So this is the corresponding curve. And you can see if you close the valves early, close the intake valve early rather, then your volumetric efficiency is quite high at low speeds, but with the speed, it drops drastically. Now, the next one, if you go, inlet valve closing at opening at 19 and closing at 10. That means so opening at 19, little earlier intake valve open and little late inlet valve closing compared to the first one. And the operation is like volumetric efficiency is not the best in the low speeds, but it gets better in the middle speeds. And again, with high speeds, the inlet, the volumetric efficiency drops drastically. And on the other hand, you can see in the third one, where you open inlet valve very early and close it quite late, then the variation is this box curve. It is like this. So if you keep the valves open longer duration before the top dead center, before the bottom dead center, then the volumetric efficiency at high speeds will definitely increases due to the ram effect. But again, if you leave it open for a longer time after bottom dead center, then its performance in terms of volumetric efficiency at low speeds will be very less because of the backflow. Therefore, you can see the intake valve timing is always a compromise of the speed. So this timing, the best timing that you want in low speed conditions is not the best timing at the high speed conditions. Now, out of this, the best curve would be this curve, the middle one. So you get the average of this and this over here, and somewhat better in the high speeds also. And if you look at the performance of that under different valve lift, maximum valve lift conditions, again, and you can see at low speeds, the lift doesn't play a significant role, but at high speed conditions, having a larger lift would always be better as far as the volumetric efficiency is concerned. So, I mean, at this small lift condition, the volumetric efficiency drops significantly at high speeds compared to the high valve lifts. Therefore, it is obvious that the volumetric efficiency is highly dependent on inlet valve open and closing timing, as well as the speed of the engine. Early intake valve closing improves the effective compression ratio. So that is when you have the valves open, when it comes to calculation of the compression ratio, the effective compression ratio includes some of these areas above the valve. So these are open. So this, when it comes to calculation of the clearance volume, some of these areas also need to be considered. Accordingly, if you keep the valve open at the bottom dead center of the piston during the intake stroke, then the compression ratio of the engine drops because these small areas open here should be included in the clearance volume. So the larger clearance volume lead to small compression ratio. Accordingly, in conventional engines, valve timing is a compromise between the speed and the load conditions. But in the modern systems, variable valve timing systems are used for better performance. Similarly, if you can look at the exhaust valve open and closing timing, so you have to open the exhaust valves early to allow gases to go out of the system through blowdown process. And at the same time, opening the exhaust valve early would reduce the expansion ratio. That is, you open the valve while the gases are expanding. So the real power that could have been extracted from the engine is reduced. Accordingly, there can be negative effects. So it's a compromise between efficient blowdown as well as amount of power extracted from the engine. And on the other hand, exhaust valve close timing depends on the valve overlap time. That is, it depends on valve overlap time. And having a valve overlap duration, particularly at low speeds, will have a negative effect of having backflow, so that the charge dilution with the exhaust gases. But it will be good when it comes to emission control, particularly the NOx emissions. And at high speeds and high loads, again, the ram effects will support this process of intake and exhaust during overlap period. And the scavenging process, that is pushing this exhaust gases as a result of incoming air into the system due to ram effect, would enable better performance at high speeds. Again, then it becomes a compromise between the speed conditions, load conditions, and the valve open and close timing. So the best answer for all these compromises is the variable valve timing. So the people have developed variable valve timing systems where you can change dynamically the valve open and close timing and the valve open durations. And in certain situations or certain systems, even valve lift can dynamically be controlled. Accordingly, you could make sure that you get the best volumetric efficiency under various different operating conditions of an engine. So this is one such system. The late inlet valve closing or the longer valve open duration would enable greater maximum power, and early intake valve close would enable better performance under low speed and low torque conditions. So these are some of the technologies used for this variable valve timing in the industry. Cam facing systems, where you can move the entire cam, offset the entire cam by a certain duration, face the entire cam by the duration accordingly. You can move the inlet valve, for example, open timing towards the top dead center, and at the same time, inlet valve closing timing will move out of the bottom dead center because it is just facing, you don't change the duration. And then there are systems which operates on the concept of switching between different cam profiles. So you can have different lifts and different durations, different open timing with these profiles, with these technologies. And there are 3D cam profiles, fully variable lift and timing systems, and electromagnetic valve drive systems. So there are the 5 technologies used. So usually this is the first generation, and these 3 technologies are widely used nowadays. And the advantages and disadvantages of each and every technology is shown here. For example, switching between different cam profiles are very good or excellent for power, but very poor for emission control. On the other hand, varying cam systems are not that good as far as the power production is concerned, but much better in torque production as well as the emissions. So likewise, each and every system has its own advantages and disadvantages. So these technologies are currently used in commercial engines. And finally, if you move on to 2-stroke engines, we all know the operation of 2-stroke engines. Basically, we have intake port down here and exhaust port up here. And there's a transport, that is the transfer of intake gas takes place from the crank casing to the combustion chamber or the cylinder. And there's a specific shape made on the piston crown, a wedge shape like this, which enables pushing the intake air towards the exhaust and make sure the exhaust gases or the burn gases go out of the exhaust port. Now, as you can see on this animation, as the piston comes down, this intake port gets closed, this valve gets closed, and accordingly the gases are compressed. Gases over here are compressed by the piston motion downwards. At the end of the downward motion of this piston, the transfer port opens and we create a pressure here. So that pressure will push air into this area. And as the air comes in, or the air fuel comes in petrol engines, then that incoming air pushes the exhaust gas out of the system. So that is how the system works. There are 4 strokes basically in any engine operation. So in 2 strokes engines, 2 engine strokes are combined together so that 4 engine strokes are completed in one complete engine revolution. So this is the valve timing or the port timing diagram of such an engine. So I'm not going to go into details of this, just for your information, you can take a close look. I hope you can now understand the basics pretty well. Now, there are at least 3 technologies used for gas exchange in internal combustion 2-stroke engines. One technology is the cross flow. That is what we just looked at in that animation. The incoming air or the air fuel mixture comes through the transfer port, and the shape of the piston enables the scavenging. The scavenging is a process where incoming air pushes the exhaust gas out of the system, and the flow is governed by the shape of the piston. In this cross-flow scavenging, you can see the transfer port is in one side of the engine and the exhaust port is on the other side of the engine. Now, the next technology is loop scavenging. So as you can see here, in loop scavenging, the transfer port as well as the exhaust port is in one side. Again, the piston shape or the shape of the piston count enables gases to go through a loop like this, and that enables scavenging of exhaust gases. Now, this configuration or the loop scavenging is preferred in small size, low cost compact engines, because you have all these things in one side so that you can make it smaller and the cost effective way. The third one is the uniflow scavenging, where instead of exhaust port, you have an exhaust valve, and there are transfer ports made across the engine. So the incoming air is pushed upwards by the inward motion of the piston, and the gases will go out of the exhaust port or the exhaust valve in this case, located up here. So this situation, now the uniflow scavenging process, both gases move upwards. And uniflow arrangement gives you more time for scavenging. Accordingly, the scavenging process could be improved. So you have more time for scavenging. So the scavenging efficiency could be improved using this configuration. All in all, as you can see, that's in 2-stroke engines, there's a mixing of air, intake air and exhaust air. And there's a greater possibility of trapping some exhaust gases inside the cylinder. Accordingly, there can be a lot of negatives or the disadvantages of these 2-stroke engines compared to the efficiency of the gas exchange process of 4-stroke engines. Now, this is a kind of a summary of what we just said and short. In cross-flow scavenging, there can be a couple of transfer ports as well as exhaust ports. And there can be situations where you have all around the transfer ports like this and exhaust ports, so that you can make the efficiency of sucking air in. You can increase the efficiency of sucking air into the system, the intake process, as well as sending exhaust gas out of the system. And in loop scavenging, also you can have many ports in one side, transfer ports as well as exhaust ports. And in uniflow scavenging, usually they are made such that circular motion is generated, a swirl is generated, in other words, so that the turbulence or the mixing process could be enhanced under uniflow scavenging conditions. So as far as the quantification of the performance of gas exchange process in two-stroke engines, we use three different approaches. One is the delivery ratio, is the air mass delivered per cycle divided by the mass would have induced into the system, that is under ambient conditions. So that is basically somewhat related to the volumetric efficiency that we have discussed with four-stroke systems. And then comes trapping efficiency, how now you can see there is a greater chance of incoming air going out of the system in two-stroke engines. So the trapping efficiency is defined as ratio between mass retained in the cylinder and mass delivered to the cylinder. Air mass delivered to the cylinder per cycle rather, and how much of air mass trapped inside the cylinder. That is the air mass retained, the ratio between air mass retained and air mass delivered. And then comes the scavenging ratio, that is the efficiency of the exhaust process, the scavenging process, that is air mass retained in the system divided by the trapped charge mass, how much of mass is trapped inside the system. And also you can recognize that the amount of charge retained or remains from the previous cycle will be 1 minus neta Cs, that is the scavenging ratio. And on the other hand, if you say mass retained in the system is MA, then MA would be the trapping efficiency into the amount of mass that could have been induced into the system under standard ambient conditions. That is rho in ambient air multiplied by the displaced volume. So these are some of the references that I considered in this lecture. So most of these books are available in the library too, and I hope some of them can be downloaded in public domain.